So the fundamental key to learning logarithms is understanding the notation. Before we start talking about logarithms, I'd like to introduce a notation you're pretty comfortable with and you've seen before in the past called exponents and radicals. There is a relationship between exponents and radicals, and it's all about the literacy in the symbols. Symbols have meaning and you need to be able to pull it out. For instance, if I take the square root of 16, that's a symbol, it has a meaning, and we can calculate the value because we understand how to read that symbol. So the first thing is all talking about what is that symbol asking us to do, and it's asking us to find a number times itself twice, that is 16. And the number times itself that's twice, that gives us 16 is 4. I'm going to rewrite that sentence then. There's another way I can rewrite that same information. 4 times itself twice is 16. So the first sentence reads, what number times itself twice is 16? And the answer is 4. The second sentence reads, 4 squared, which really means 4 times itself twice is 16. Both of these sentences contains the same information, but they're presented in different ways. Let's look at some more. The cube root of 125. Cube root of 125 is 5. Because, what was it fundamentally asking us? What number times itself 3 times is 125? All about being able to read the meaning in the symbol and understand what's being asked. So, 5 is the answer to this question because 5 cubed is 125. So that second sentence has the same meaning as the first sentence, but it has a different focus in the sentence. Now, I'm going to write these sentences out in their generic format. This sentence is equivalent, let's see what I'm saying, the nth root of b equals a. Why? Because a times itself n times is b. These two sentences say the same thing. One is in radical form, one is in exponent form, and notice it changes where the focus of my sentence is. The first sentence has a focus on A. The second sentence has a focus on B. Notice how they match up to here. 4 squared is 16. 4 squared is 16 because the square root of 16, is 4. So I'm just using the general pattern now with the A, the B, and the N. So far, so good? Notice there are 3 values in this sentence. N, A, and B. Right now I have 2 sentences say the same thing but in a different focus. The radical format focusing on A. The exponential format focuses on B. I'm missing a letter right now. I need a focus that allows me to talk about N. What is N? Well, I can say it in words. N is the exponent on A that gives us B. Now I need symbols in math that say the same thing. N is the exponent I put on A to get the value B. That is a logarithm. It takes that one sentence that has 3 pieces in it and now allows me to focus on that third piece. So, let's take a look at this. If I want to go from A cubed equals, well, let's not do that way. Hang on a second. Don't want to go with, I want to go to n. So let's go with 5 to the n equals 125. One of our statements up above. So 5 to the n equals 125. I would like to now change the focus of this onto the exponent n. So before we've had exponent form and radical form to change our focus. Now we're going to talk about logarithmic form. N is the exponent I put on the 5 to get the value 125. This we know how to calculate. 5 to the first is 5. 5 squared is 25. 5 cubed is 125. So the exponent I'm looking for is 3. That's the exponent I put on a 5 to get 125. Let's look at this logarithm. First of all, I'm going to read what I'm looking for. I'm looking for the exponent I place on a 2 to get the value 8. That exponent is going to be a 3. I can take this equation here and take it out of exponent form and put it into logarithmic form. By doing so, it changes the focus. Now I can say x is the exponent I put on 10 to get 100. And I know that that exponent is in fact a 2. Why? Because 10 times 10, or 10 raised to the second, is in fact 100. Log base 10 of a is often simply written log of a. Whenever you don't see the 10, it does not mean you don't have a base. It's just the common log. And because it's so common, we frequently just don't write the 10 there. Sometimes you'll see the 10 written there. Sometimes you will not see the 10 there. The nice thing about the common log, it's one of the 2 types of logarithms your calculator can handle. Another nice thing about the common log, it's very easy to calculate in your head. For instance, I can look at this logarithm and I can evaluate it using a little trick. I'm going to say that this logarithm is approximately, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm going to say it's approximately 11.3, maybe 5. Let's pull out the calculator, see what the calculator says with that, and I'll show you how I did it. Just a basic little trick. So go ahead and pull out your calculator at this time. So, what did you get when you plugged it in the calculator? 11.4? Wasn't a bad trick off my top of my head. 11.4, 11.35. How did I do this? To be able to calculate a logarithm using the technique, I'm going to show you a little pattern you learned way back when in math. 10 to the 0 is 1. 10 to the 1 is 10. 10 squared is 100. 10 cubed is 1,000. I want you to notice how many trailing zeros there are behind that 10. 3, 2, 1. No trailing zeros. So, automatically I know 10 to the 22nd is 1 with 22 zeros. So far, so good? Now, let's go back to this number. And I'm going to look at a very simple number to evaluate. This is a 1 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 trailing zeros. Which means the exponent I put on a 10 to get that number is exactly 11. So far, so good? Now, let's look at another number. This is a 1 with 12 zeros trailing it, which tells me that I need an exponent of 12 on 10 to get this number. So this number has an exact value of 12. Perfectly exact value of 12. Notice, the first number is smaller than the number I was trying to estimate. The second number is clearly bigger than the number I was trying to estimate. So the exponent I was looking at had to be bigger than 11, smaller than 12. Everyone okay with this? Okay, I'm going to use this technique to answer this question. Find two consecutive integers a and b such that a is less than log of n, which is less than b, for the given number, log of 175,621. So to accomplish this, all I'm going to look at is this number. I know this number is smaller, but it is exactly 1, 2, 3, 4, 5. So 5 is smaller than this logarithm. This logarithm has a number bigger than 5, yet smaller than 6. How do I know it's smaller than 6? Because 1, 2, 3, 4, 5, 6. If I put 6 as an exponent on 10, I clearly get a number bigger than 175,621. If I put 5 on an exponent on 10, I get a number that's clearly smaller than 175,621. So 5 and 6 are the two integers I'm looking for. Consecutive means one right after the other. When you're simplifying with logarithms, you have to remember that we're doing the same order of operation, PEMDAS. Please excuse my dear Aunt Sally every single time. So we just have to figure out where logarithms fit in this location. Well, first of all, I'm taking the log of 100. So one of the things we can do if we wanted to is we could put a parenthesis around that 100. Even though it's not always written there, it's always an implied set of parentheses. This is important because on my PEMDAS, I start with my parentheses. So the very first thing I need to do to simplify this is deal with what is the log of 100. What exponent do I put on a 10 to get 100? So this number is 2. And now I continue to simplify. I'm going to do my multiplication and division, then addition and subtraction. So the order of operations doesn't change. You just need to figure out where your logarithms fits into that.